Hi friends, welcome to GMK tutorials. In this video, we are going to see about the metal oxide semiconductor field effect transistor. In our previous videos, we will discuss it regarding the junction field effect transistor as well as bipolar junction transistor, right? Now, when we come to the metal oxide semiconductor field effect transistor. So guys, before going to this topic, so please I request you all of you, please subscribe our channel. Please share and like and subscribe to your friends as well as you can share your friends also. Okay. So thank you for your support up to now. Thanks a lot for you, each and everyone, for your kind support and all those things at any situation. Okay. Now let us move on to the topic. Metal oxide semiconductor field transistor is one of the most used device in the fabrication of the most of the chips nowadays, right? I think most of the boards can be fabricated with the help of a field effect transistor. Because of these field effect transistors have some more advantages compared to the bipolar junction transistors. Okay, so that's why we can prefer this metal oxide semiconductor field is used in so many applications also. That points are some of the points already discussed in the before entering the JFEC topic, right? So let us see in this just we will confine to this topic. So metal oxide semiconductor, the name itself represents metal oxide semiconductor field effect transistor. So let us see, it is just you have initially you have to take a peek at the let us see the construction of the MOSFET first. It is a enhancement MOSFET. The enhancement MOSFET, here we are studying about the enhancement MOSFET. So in this one, let us see first one p-type substrate. Just we will take, it is a p-type p-type lightly doped semiconductor material, lightly doped semiconductor material. So in the p-type semiconductor material, just you have to two highly diffused islands are deposited on the top of the surface. That is generally it is called as a 1n plus region. It is a highly doped n plus region. Okay, so both. So as well as on the top of this one, just you have to fabricate it. This one is nothing but SiO2 layer. This SiO2 is layer also called as a SiO2 layer. This is act as a insulator. On the top of the SiO2 layer, just you have to deposit the polysilicon. Okay, polysilicon or polycrystalline also. Polycrystalline. So this is generally called as a metal contacts like aluminum. Therefore, in this overall construction, we will observe three important things. That is nothing but a metal. Second one is nothing but a oxide. Last one is nothing but semiconductor or substrate. So based on these three material, it forms a metal oxide semiconductor. So that's why we can call as a metal oxide semiconductor field effect transistor. Here metal is nothing but like aluminum. Here metal is nothing but like aluminum, which is used for connecting the devices, as well as oxide layer means that SiO2 layer. SiO2 layer is also called as an oxide layer. It is act as a insulator. Last one is nothing but a piece semiconductor. It is also act as a conducting material, or it is also called as a diffusion. Okay, so this is a very important construction of the p-type n-type enhancement type semiconductor. Just we don't want to discuss it. In case of the initial general construction of the MOSFET, we don't have any channel is existing in between the source and drain, right? If we want to work the corresponding metal oxide semiconductor field transistor, obviously there is some current flow from source to drain or drain to source, right? If you want to if you want to flow from the current from source to drain or drain to source, obviously there is some channel will be existing in between the source and drain. Initially, in case of the enhancement MOSFET transistor, we don't have any channel at this instant, but we can enhance the channel, or we can create the channel in between the source and drain by applying the some of the suitable voltages in the gate terminal. It forms a one inversion layer. We can also call this a channel layer. Then there is existing a some current conduction will be possible. So for that purpose, let us see some of the points related to this one. So in this case, generally we know that the base semiconductor material is used for the MOSFET fabrication. Okay, the base of the material is a material used for the MOSFET is nothing but semiconductor material is used for the fabrication of the MOSFET. This metal oxide semiconductor forms a basic structure of the MOS transistor that is shown in the figure. The three conducting materials are used in case of the three conducting materials are there in the construction, that is nothing but one is nothing but a metal, second one is nothing but a polysilicon, and third one is nothing but diffusion. The three metals are act as a conducting material in the MOSFET, right? As well as the aluminum material is used as a metal, and the polysilicon is used as a conducting material in between the source and drain and gate and source, like this, right? The insulating layer is made up of SiO2, that is nothing but silicon dioxide. Okay, that is nothing but a silicon dioxide. This is the construction of the metal oxide semiconductor field effect transistor for the enhancement mode. Okay, just we will see that this is a basic structure. Actually, just we will see about the what is meant by enhancement mode. Okay, right? Let us see. Okay, this is a enhancement NMOS transistor type substrate. So let us say in this in case enhancement NMOSFET, if you want to fabricate the NMOSFET, first of all initially you take a P-type substrate. That P-type substrate is a lightly doped material. So whatever we discussed in the previous one, as well as these N plus regions are very highly doped regions. Okay, that the highly doped regions are also act as a source and drain terminals in case of the NMOSFET enhancement. So let us say here, observe this one. We don't have any channel in between these two. Okay, no channel, no electrons are flowing in between these two. So for that purpose, if you want to work the corresponding transistor in a proper way or proper operational device, if you want to act as a proper operational device, compulsory the current is flowing from source to drain or drain to source through the corresponding channel. As well as, so for that purpose, let us say initially we can apply some suitable voltage. That means VGS is connected to positive terminal of the battery and source is connected to the negative terminal of the battery, right? At this moment what happens is that when the positive voltage is connected to the gate terminal, at the time the positive voltages are deposited, the positive charges are deposited on the polysilicon. Okay, let us see just that overall view can be represented like this. If you are taking it is a SiO2, it is nothing but a polysilicon. Okay, so when we are connecting this terminal to the positive voltage, what happens is that some positive charges are deposited on the polysilicon. Due to this one polysilicon, due to the polarization, negative and positive charges are created on the silicon dioxide layer, right? When the positive voltage is created across the silicon layer, what happens is that some electric field will be produced, as well as due to the, so this is all just if you are seeing like this. Okay, this is a drain part, this is a source part, right? When the positive charges are accommodated the silicon dioxide layer in the bottom side, at that time due to the positive charges of the accommodated in the SiO2 layer, these positive charges repel the positive ions present in the this region. That means these are moved in this direction. Therefore, they at this place only negative charges are takes place. Okay, so when the gate voltage is rising still, obviously more number of electrons are present in the, if the gate voltage is further increasing, more number of electrons are present in this region. Okay, then so at a minimum voltage, by applying some suitable voltage at the time, the complete electrons are placed in between the source and drain region. This is generally called as a channel. Okay, therefore by applying some suitable voltage, the electrons are accommodated here. We know that all of you having very well known that one. In case of the p-type semiconductor material, the majority charge carriers are holes and minority charge carriers are electrons, right? Right, I think all of you having some basic idea about this one. Just whenever some positive voltage is applied at that time, what happens is that the positive charge carriers are accommodated the polysilicon. Due to the polarization of the corresponding that one, some negative and positive charges are takes place on the SiO2 layer. When the positive charges are placed in this bottom region, what happens is that whatever the p-type semiconductor majority charge carriers that are repelled by the positive terminal of these charges. Therefore, all positive charges are comes down like this. Okay. Therefore, it leads to only minority charge carriers are takes place in this region. When we are supplying the more number of gate voltage, more number of electrons are accommodated at that place, it forms as a one complete path for source to drain. That channel is generally called as a channel. Okay. Moreover, if you are observing this one, we can also come to here one more important point. That is nothing but this complete p-type material is nothing but holes are the majority. Holes are majority charge carriers, right? As well as the electrons are minority. Electrons are minority charge carrier. Actually, in case of the p-type semiconductor material, the majority charge carriers holes means but the channel is existing due to the minority charge carriers. It is the opposite to the majority charge carrier. That's why it is called as a inversion layer. Okay, that's why it is called as a inversion layer. It is also called as a channel. Okay, so whenever the channel is existing between the source and drain, there is a possibility for movement of electrons from source to drain as well as drain to a source. That is generally we can call as a drain current, right? So this is the thing only. That means if you want to devise any device, obviously the corresponding channel we need to control. Then only it is used as a some active device. Then else it is also use it for a more number of applications. In case if you are not in a position to control the channel electrons or channel in the corresponding NMOS, enhancement or depletion MOSFET, whatever it may be, whatever the MOSFET, if you are not in a position to control the corresponding channel, that device is not suitable for more number of applications. So from compulsory, whenever it is possible to control the corresponding channel region only, then only it acts as a very good device for the different application. I think this video will give a very more information regarding this one, I think. Okay, so let us see some of the points related to this one. According to the mass action law, what states that according to mass action law, according to mass action law, what is that? Np is equal to Ni square. Eccentric concentration is equal to square of certain is equal to square. So what happens is in this case? In this case, P regions, P holes are decreasing downwards. That means P is decreases means that what happens is that P values decreases means that compulsory this value is satisfied for the semiconductor materials. This N value is quite increases. In case if you want to match this one, compulsory if the p and the holes means decreases means that compulsory electrons are increased. Therefore, that's why the more number of electrons are present in the corresponding channel region. As well as if you want to form the some channel in between the source and drain, compulsory we need some minimum voltage. That voltage is generally called as a threshold voltage. Threshold voltage, that is around 2 volts approximately. It is a 2 volts to form a complete channel in between the source and drain. Suppose if you are still increasing the, so this is some of the situations. Let us consider when VGS is equal to, when VGS gate to source voltage, VGS is equal to 0, VGS is equal to some 0, VDS is equal to 0. At that time, no channel is existing in between the source and drain. At that time, it acts as a cutoff region. Okay, at that time, it acts as a cutoff region. When the VGS voltage is increases to some positive voltage, VGS is greater than VT and VTS is equal to 0. At that time, it is also act as a ohmic region. Okay, it is also act as a ohmic region. That means at that time the corresponding voltage is 0, but based on the increasing on the gate to source voltage, the corresponding drain current is also increased, right? So at a particular point of time, the corresponding gate to source voltage is also act as some constant value. Okay, it is independent on the corresponding, independent on the VDS voltage also, right? Still, if you are increasing the VGS value is more and more, VGS value is greater than VT, that is nothing but we can also defining like this at the time, more and more, if the VDS is also increased, VDS is also increased, what happens is that more number of, more current is flowing, more current is flowing, because of when the VGS value is increases means that more number of electrons are accommodated. That means electrons are, electrons increases means that current is also increases. This is the reason behind that one, right? So let us see the graph related for that one. Graph related for that one, the drain characteristics as well as the VDS, which will give say some of the observations related to that one. Okay, let us see here, drain current characteristics. Just I will draw the graph here. Initially, if you are increasing like this, it is moving. Just I will take, this is nothing but drain current. It is in terms of a milliamps. It is generally called a VDS, drain to source volt. It is in the form of a volts. Okay, as well as these are the VGS voltages. When the VGS voltage is equal to 2 volts, 4 volts, 6 volts, or 8 volts, that means this is in the increased version. Then only the channel is existing between the corresponding terminal. This is nothing but a VGS, right? Gate to source voltage, right? Now this region is also act as a ohmic region. Okay, this region is also act as a ohmic region. This is generally called as a saturation region. This is called as a ohmic region. Okay, this is generally called as a cutoff region. In this cutoff region, why it is cutoff region? At this point, or at this point, the corresponding drain current is VDS is equal to 0. At that time, VDS voltage is also low. That means a very less number. That is nothing but when VGS voltage, VGS is less than VTH, what happens is that no channel is existing. No channel is existing means that no current. No current means that it acts as a half. So it is also act as a cutoff region, right? So we will move for some more details regarding the ohmic region. Okay, ohmic region. So ohmic region, in case of the ohmic region, it is controlled by the VDS, for VD is equal to ohmic region. Ohmic region. So in this case, drain current ID is controlled by VDS for VGS is greater than VT case. So it depicts the sum of the equation VD is equal to 2 times that of K into 2 times that of VGS minus VT into VDS whole square. So if you are taking VDS as a common factor, ID is equal to VDS into K 2 times that of VGS minus VT minus VDS. This is the equation. So from this equation, there is a some so these two, ID is directly proportional to VDS. That means if the drain current is VDS value is increases, as well as the corresponding ID current is also increases. This is a relation between the corresponding drain current as well as the corresponding supply VDS voltage, as well as where K represents the mu m Cm W by L, where L is nothing but length of the channel. Length of the channel. It is a order of around 10 micrometers, as well as W is nothing but width of the channel. Width of channel, it is around 100 micrometers. Okay, so the unknown parameters in this case, the ohmic region is also some of this, where that is nothing but mu m. Mu m is nothing but surface mobility. Okay, mu m is equal to surface mobility. Okay, surface mobility. So mu m is a very quite low. Okay, it is also mu m is very small value. Mu m is 600 centimeter square Vs. So here, in case of the mobility of the electrons, in case of this region is very small compared to the mobility of the electrons is here. Mobility of the electrons is mu m is very less. It is in the order of around 600 cm square, right? Because of, if you are comparing very completely, that value is very high. That is nothing but around 1500 around also. Okay, but in this case it is around okay, as well as the why the mu m is low means that the scattering of the electrons from the surface from the trapped charges in the oxide layer. Okay, then the compared that value is very less count, because of we are taking only part of the region. As well as one more parameter is nothing but Cm, that is nothing but mu s into mu nr and bo by tox, where tox is nothing but oxide layer thickness. As well as mu s is nothing but dielectric constant. Of oxide layer. As well as mu epsilon is nothing but permittivity of a free space. Right, these are the some of the unknown parameters. If you don't all these complete parameters, we can write the corresponding k also in terms of known parameters. K is equal to id on by vgs on minus vt whole square. If you don't have all these parameters, we can, if you know the id and vgs values, we can directly calculate the k value from the given data id value as well as. So this is regarding the ohmic region in case of the drain current. That means in the ohmic region, as the vgs voltage is constant, at that time more number of currents are accommodated in this region, right? Let us see here, just the diagram itself, it represents when the VGS voltage increases, what happens is that here the drain current is increases some more, and it may at the VGS is equal to voltage, as well as the drain current is increases still at point of time it maintains some constant value. That means it maintains some constant value. Okay, so coming to the saturation region concept, so saturation region, next one is nothing but a saturation region. So in case of the saturation region, the given equation is nothing but VDS is greater than or equal to VGS minus VT. Compulsory this is satisfied, then only it is comes under the saturation, because of it is a border of that one. VGS minus VT is equal to greater than VGS, then only it is entered into the. So just in this case, we have one equation is there. ID is equal to K times that of the VGS minus VT. So if you observe this one, in case of we don't have any VGS term is there, that means ID current is independent. ID current is independent on VDS. Independent on VDS. Okay. Therefore, that is related for the saturation region. Just we can also call as some of the things, some early voltage concept is also there. Just I will draw the graph for this one. Just I will, if you are taking Okay, generally, if you are treating this one as a minus 1 by lambda, okay, this is nothing but a drain current ID. This is nothing but a VDS. This is a VGS voltage is increasing like 2 volts, 4 volts, 6 volts, and 8 volts. Right? This 1 by lambda is generally called as a early voltage. 1 by lambda is called as a early voltage. Early voltage. So the relation between the corresponding early voltage and drain current ID is equal to K into VGS minus VT square into 1 plus lambda into VDS. Okay, as this VDS value is very small, therefore it is neglected here. Okay, 1 by lambda is also very small. Okay, so this is very small, so it is neglected. Okay, therefore finally we have an equation is there, that is in terms of small, that is nothing but ID is equal to K times set of VGS minus VT whole square. This is the final equation for saturation region. Coming to the cutoff region, the cutoff region is also very important, guys. So in this cutoff region already we discussed indirectly, that is nothing but cutoff region. So in the cutoff region, what happens is that when the VGS voltage is less than VT, VT is nothing but the minimum voltage is required to form the channel between the source and drain. But when the supply voltage, VGS voltage is less than that of the threshold voltage, no channel is forming in between the source and drain terminal. Therefore, no current is flowing from source to drain. Therefore, it is an act as a half condition, that is nothing but cutoff region. So this is related to the metal oxide semiconductor field transistor, guys. Guys, it is very easy, guys. If you know the one logic, definitely you can form the P-type enhancement semiconductor Mosfet metal oxide semiconductor field effect transistor. Just you can change the corresponding substrate only. So P substrate is replaced by the N substrate. N wells are replaced with the P plus as well as gate supply voltage. Just you have to apply this some negative voltage, that is nothing but minus VGS. Then obviously the electrons are repelled due to the corresponding charge carriers present in the SiO2 layer. Only positive charges are accommodated. In case of the PMOS enhancement mode, PMOS enhancement PMOS MOSFET mode, only the charge carriers are positive charge carriers are the responsible for the channel formation. Okay, so this is a very brief idea regarding the NMOS metal oxide semiconductor field effect transistor. I think it is the very easy, guys, if you are understanding very clearly. Okay, so thank you for watching GMK today. Thanks a lot.